Good morning or good afternoon, everyone, depending on where you're joining us from, and welcome to today's webinar. My name is Kalina from Business Review, and I will be your host today. It is our pleasure to have Eppendorf AG with us today, who will be presenting this webinar titled Troubleshooting in Bioprocessing. Today's guest speakers are Ines Hartmann, Application Specialist Cell Handling at Eppendorf AG, and Ankita Desai, Bioprocess Field Application Specialist at Eppendorf North America. I would like to welcome you to our webinar platform on 24. You will notice that this webinar is browser-based, so if you disconnect for any reason, please just click on the link that you received via email to rejoin the session. In order to ask any questions, you can do so by using the Q&A widget at the top corner of your screen. You just need to submit your question. Towards the end of the session, we will take some time to address any questions or thoughts that you may have. Please use the yellow help widget if you require any assistance, and you can move, resize, and maximize any of the windows in front of you to get a better view of the slides. But now, please allow me to welcome Ines Hartmann. Ines, over to you.
Thank you, Kalina, and hello from Hamburg first. Welcome also from my side. Ankita and me will shortly maybe introduce ourselves. So yes, my name is Ines Hartmann, and I'm cell handling application specialist responsible for shakers and mixers, so everything that swirls and shakes. And I work at the Eppendorf headquarters in Hamburg, Germany. I joined the company in 2008 and have worked in several topics in cell handling, liquid handling, and consumables. And I shortly hand over to Ankita to present herself.
Thank you, Ines. Hello, everyone. Welcome to today's webinar. My name is Ankita Desai, and I'm the Bioprocess Field Application Specialist for Eppendorf, working from the West Coast in the U.S., so from California. And I've been working with Eppendorf from 2017, so I've been working mostly with the bioprocess systems as well. Back to you, Ines.
So our topic for today is troubleshooting in bioprocessing, and be prepared also with your mobile phone. We will have a couple of QR codes in the presentation, so you can. This one leads you to our bioprocess handling solution website, and in the following slides we will have some links to our application notes if you want deeper knowledge, as we have only 45 minutes, so not enough time for troubleshooting. So what you see here is the basic steps of a bioprocess workflow. It consists of first the pre-culture or inoculum generation, starting usually in a shake flask. Second, the bioreactor must be set up and prepared for cultivation. That includes not only selection of the system, of course, but the sensor calibration and sterilization. And once the bioreactor is prepared, medium can be inoculated, or cells can be inoculated in the bioreactor, and the actual bioreactor culture starts. And with this, the growth must be monitored and controlled. So maybe you know this, you're eager to start, have your culture prepared, and are ready to run your process if, yes, there would not be these daily challenges you maybe all encounter and know, and these hurdles of daily life. So vessel and impeller selection, DO, pH control, foam formation, upscale issues, just to mention a few. So first we have a small poll we would like to know. So what are your daily challenges in bioprocessing? Click on what you encounter, system selection, for instance, what impeller, probe calibration, pre-culture, control of DO or foaming issues. Just click on it and push on the send button or submit button, and then we continue. So I give you some time to select. Okay, I see some of your system selection is an issue, poor growth, control of DO and pH, and scale up. Okay, that's good. So we will go through the whole workflow and have some tips on troubleshooting and look at different challenges in all these steps. Let us start shortly with troubleshooting of the pre-culture. So the pre-culture, as you all know or may use is generated usually in a shake flask. For higher volumes, you go to a seed fermenter. And different than bioreactors, stirred culture, oxygen passes to the culture by diffusion via the liquid surface. So shaking increases the surface area for diffusion by creating this swirl movement. And this enlargement of the swirl introduces more oxygen. There are several influencing factors as well in shake cultures. For instance, the vessel type, the fill volume, and on the shaker side, of course, you can decide between different shaker orbits, for instance, so shaking diameters, and the agitation speed. So one challenge is often poor growth, as you also mentioned. So how to improve growth rates and also maximum yields? We talk here about shake flasks. So baffles, of course, can increase growth rates and yields. Baffled flasks have defined cavities introduced in the bottom of the flask. They create a curl leading to more oxygen introduction into the culture. And but the downside is that they may also give more variable results from flask to flask. So try best first for pre-culture generation unbaffled flasks, and also when you use baffled flask, you must add antiphon, usually when you work with higher speeds. Second, you can also play with the fill volume. So keep fills, especially when you work with oxygen-limited or fast-growing bacteria. Keep them at maximum 20% of fill volume for mammalian cells, as they are not as fast-growing and consuming oxygen. 30% is optimal usually. There are also special flask designs, ultra yield or optimum yield, for instance, that allow higher fills, but usually they are paired with high speeds. Third, also increased agitation, of course, is another optimization factor in shake culture. So increased agitation can, as you see here, positively impact especially bacteria growth, but usually does stress mammalian cells, so does in the other side a negative influence. Also, the shaker orbit has an impact that should be looked at, for instance, when changing from one orbit to another, so changing the shaker, for instance, the RPM can usually be easily adjusted. Second troubleshooting for pre-culture would be reproducibility. So the aim is to have a reproducible inoculum with same vitality. So first, it is good practice always, no matter what culture you work with, to record a growth curve, to analyze the behavior of your culture and to know where the logarithmic phase, it's here, with the most amount of little cells is. So that would be the second tip. Use pre-culture in its late logarithmic phase to have as many little cells in the inoculum of the bioreactor or fermenter. That would reduce, or good chance to reduce, the lag phase. For bacteria, so inoculum is prepared from the preservation culture always and activates the cells prior their usage for fermentation. So for microbiology, it is beneficial to use a single colony from a freshly streaked agar plate to inoculate a liquid bacterial culture and not go directly from the glycerol stock, for instance. That prevents not only from a potential enrichment of contamination if you have one in stock, it also results in a better synchronization and avoids genotypic variations. Also, from the small liquid culture, volumes can be further expanded, of course, to larger flasks depending on the required inoculum volume. It's also good to use defined growth windows. Schedule your growth to harvest at the same OD, and check with your shaker if there is a programming function. Some shakers have this. Then you can program temperature for growing 37 degrees, and in the end or in the beginning a cooling phase to preserve the culture and stop them from growing. For cell culture, the vial is thawed according to cell-specific SOP in a small volume, either static or shaken, and expanded usually by splitting cells. Cells are usually very sensitive to cryopreservation, and often the freezing is standardized but not the thawing. And the water bath is still, let's say, the most applied method to thaw cells. You may look in other methods, for instance, by using a thermomixer, which is water-free, which allows to thaw more standardized, reduce the contamination as no water is there, and also you can handle multiple vials in parallel. Just if you're interested, here's the first QR code you can scan. So, finally, pre-culture grow well and reproducible. So it's going to be the selection and setup of a fermenter or bioreactor. And with this, I would like to hand over to my colleague Ankita.
Thank you, Ines. So to start with, a basic bioprocess workflow will start with the bioreactor setup. So the first things to look at is the impeller type that will work best with your cell line, considering the oxygen transfer rate, which is actually very optimal for your cells. Next is to prepare the reactor in parallel to the pre-culture or the seed train. Now, preparing the bioreactor requires some critical preparation steps. So the first one is checking and maintaining the sensors. This, I would say, is one of the most critical steps for the entire run. Both pH as well as DO sensors need to be carefully checked for, first of all, any damage to their tips, as well as ruptures, especially in the case of DO membrane, as of course a damaged sensor will not read or respond correctly, causing various issues mid-run. It is very important to inspect the sensors before setting up the vessel and autoclaving in case of glass vessels. The next step is connecting sensors, feed and harvest lines, as well as adding the temperature control. So followed by the calibration of the pumps to give you an accurate flow rate, calibrating sensors like pH is very critical. Now, except for the DO sensors, which are usually calibrated post-autoclave step directly in your media, the next step would be to actually sterilize everything by autoclaving in case of reusable glass vessels. And then lastly, you will program the controller to set up all your gassing strategies, automated feed profiles, automated temperature shifts, etc. And then, of course, if you're using single-use vessels, the entire assembly, autoclaving, disassembly, and cleaning steps are eliminated, thereby reducing your turnaround time and also saving labor and time-related costs. So the first major challenge that we will talk about today is with respect to problems during sterilization and setup. So to preempt these issues, some of the things need to be checked and fixed if required before the autoclaving step. So the first thing is the O-ring seals. The headplate consists of multiple small parts that are very critical to maintain the sterility of the reactor. So O-rings are one such component. So always make sure that the O-rings are not damaged or bent or deformed in any way. If these O-rings are damaged, then it will compromise the sterility of the run, since there is no longer an airtight connection between the headplate components and the vessel. The next thing to focus on is whether the tubing for various liquid additions or your harvest lines, as well as the gas inlet or outlet tubings, are not bent in any way. Filters are another focus point in this step. Always check whether both the exhaust and gas inlet filters are in good condition. So which means that you should check that they are not wet, meaning no water or media accumulation, since they also need to be autoclaved with the vessel assembly, especially for glass vessels. So it's important to make sure that the tubing, exhaust tubing, is properly tightened on the head plate. Another step is the sensor check and preparation, as we spoke about in the previous slide. One also needs to ensure that in case of a polarographic DO sensor, that an unexpired DO electrolyte solution is filled into the membrane cap before inserting the sensor into the head plate. The next part one needs to check is that the impeller and the sparger height are correctly adjusted, since this is not something that can be changed after the autoclave step. And lastly, you will go ahead and add cap to the pH and add aluminum foil to the open sensor outlets on the head plate. Again, if you're using single-use reactors, then you eliminate the entire assembly or the autoclave step. So next we take a look at the motor, which is the obvious part of the connection. And then you have your impeller, which are both important in order to maintain the agitation and aeration, since they both affect the oxygen transfer rate within the vessel. So which in turn is of course crucial for your cell growth. So the motor is externally located and is essential to controlling the stirring speed of the impeller. Now the impeller itself will influence the medium flow within the vessel. So for example, as we see in the screenshot, the Russian impellers have flat blades which are set vertically along the agitation shaft, and they lead to radial flow within the reactor. Meaning that the fluid is pushed away from the impeller's axis and towards the vessel wall. Looking at a marine impeller, it has its leading face, which can be concave or flat, whereas the back ends of these impellers are convex. So this type of an impeller leads to axial flow within the reactor, meaning that the fluid is pushed up or down along the axis or the shaft of the impeller. In case of a pitch blade, a typical pitch blade impeller, they have flat blades which are set at about 45 degrees angle, and this actually produces a combination of axial and radial flow. So along with the shape and the angle of the impeller setup, the orientation of the impeller is also important. The orientation of the impeller, meaning whether it's a left or a right-handed impeller, and its agitating direction will determine whether the flow of the direction of the axial flow is up or down. Now, a right-handed impeller option will push the fluid in upward direction towards the top of the vessel if the agitation is used clockwise. Whereas if you do a left-handed option paired with a clockwise agitation, will push the fluid downwards. So therefore, when you're positioning these blades on the impeller shaft, in case of the glass vessels, it's important to know which direction your impeller will be turning, clockwise or counterclockwise. Now, the idea is to position these impellers in such a way that the flow areas will overlap and not lead to any dead zones within the vessel. So you want to maintain uniform agitation and flow in your vessel. The other aspect is to choose the right type of motor required for agitation. So based on the agitation speed, vessel type, power input, etc. So most of the modern motors are bidirectional and will allow for clockwise and counterclockwise agitation. The next troubleshooting step we will talk about is the impeller selection. So this is largely dependent on the cell line that is being cultivated. So for a typical fermentation run, which has very high oxygen demands, it is not damaged much by high shear forces, and these cells require higher agitation rates. So in those type of cultures, like E. coli, typically a Russian impeller is largely recommended, which meets all these demands. On the other hand, when you're working with typical mammalian cell culture operations like CHO cells, you need low shear stress so as to not damage the cells. You need lower agitation speed, a good mixing, as well as low oxygen demands when you compare it to a fermentation run. So for any typical cell culture operations, pitch blade impellers are largely recommended. All in all, the idea is to actually maintain a balance between your shear stress and suspension homogeneity for the purposes of ensuring uniform oxygen, temperature, and nutrient distribution within the culture. So some of the unique processes or applications require some specialized impeller systems. So for example, a cell lift impeller. So this type of an impeller typically provides circulation to microcarrier-based cultures since it is an ultra-low shear impeller. So the flow is caused by the 3 discharge ports located on the impeller shaft. This type of an impeller has the rotation of these ports, which creates a low differential pressure at the base of the impeller tube, which lifts the microcarriers up through the tube and expels them out through its ports. So this kind of a continuous recirculation loop keeps the cells uniformly dispersed throughout the vessel. The second type of special impeller is the spin filter impeller. So this type of an impeller is basically acts as a retention device, commonly used to keep or retain cells inside the vessel during continuous or perfusion culture operations. So these spin filters are again low shear. They have marine plate impellers, which are designed specifically for suspension and microcarrier applications. So it has kind of a screen cage surrounding an impeller shaft with very small filter pore openings so as to retain the cells in culture and allow for easy media exchange. And the third type of impeller is a packed bed impeller, which is basically used like a packed bed basket impeller used in the manufacture of secreted products, which you can do either from anchorage dependent or suspension sculptures. So enclosed between the screens in this impeller is a bed of fibrocell discs, which serve as a solid matrix support for cell growth and attachment. Here is a QR code for an application note that details the choosing and how you should choose different impellers for your process. Next consideration is heating. So what can we do against excessive heating or local overheating? Now, different systems differ in heating precision. So that is how fast or how accurate it can happen, as well as the price. Now, typically in microbial cultures like E. coli, they are exothermic. What this means is as the culture grows, it produces heat. This means that in case of E. coli, it is recommended to have several cooling mechanisms available to maintain the culture at the desired temperature set point. Just to give you a rough idea, about 1 liter of E. coli produces about 150 watts of energy. So if you remember the heat of an old 100-watt light bulb, you can imagine that if this heat wouldn't be controlled, it would then end up harming your cells. Which is why the heat load should be calculated, taking into consideration the heat production rate, the reactor liquid volume, the specific growth rate of your cells, biomass concentration, as well as your yield. Then the heat transfer methods can be applied accordingly. Now, heat transfer can either be done externally or internally. So for large-scale reactors, certain internal methods should be used because only these internal methods can soak up heat in such large quantities compared to external methods. While small reactors require only external cooling jackets or external cooling coils, which have the advantage mainly of being free of cleaning problems. So in internal heat transfer methods, they are usually a little difficult to clean and they can be easily fouled by the cell growth on the surface. Now let's take a look at the various parts of the bioreactor and what they are responsible for. So let's start with the most obvious one, the motor, which is on which you can see in the screenshot here. So the motor controls the agitation, which needs to be precisely controlled and has a huge impact on the culture behavior. So this motor actually is what helps in ensuring uniformity in culture with respect to temperature, oxygenation, as well as your nutrients. The other parts are your sparger, which is responsible for inserting gas into your vessel. The next part is aeration, which is how you will actually insert different gases into your reactor. And lastly, your sensors, which are going to read your key process parameters in your run. So the next factor to look at is the aeration method. So how do you decide on an optimal aeration method for your culture? Now, the answer depends largely on your cell line or your process. whether you want to be using submerged gassing or which is basically adding gases to your culture so they form small bubbles in the liquid, which helps transfer the gas to the culture. So this type of a gassing method gives you better oxygen transfer due to a high surface area to volume ratio, which is made possible because of bubble formation. Now, different types of sparger options are available, like a micro sparger or a macro sparger, among others. So basically, depending on the type of the sparger, the size and the number of bubbles changes. For example, if you're using a micro sparger, they give you large number of small size bubbles, thereby providing a very large surface area to gas transfer, leading to actually very high oxygen transfer efficiency. However, the downside of that combination is that it leads to excessive foaming, which could then end up potentially blocking the exhaust filter and also it could expose your cells to more shear stress. On the other hand, when you look at a macro sparger, it gives rise to a small number of very large bubbles. This leads to less oxygen transfer efficiency, but it doesn't cause excessive foaming and it potentially doesn't harm your cells. So depending on the process and requirements, you can choose between different sparger options. Now, the other method to consider is the headspace gassing. So this type of gassing method adds gas to the overhead space without causing any bubble formation. However, due to the limited surface area to volume ratio, this headspace gassing could potentially lead to poor oxygen transfer, which would then end up being an issue during scale-up, as headspace gassing will no longer be sufficient to meet oxygen demands at larger scales. Lastly, the other option is to use mixed gassing. That is both the headspace and sparging, which is often used in cell culture operations, where sparge gassing is used to maintain dissolved oxygen and pH, and headspace gassing is used to maintain positive pressure in the reactors. So the next part to think about for aeration is the gassing strategy. How do you choose the best gassing strategy in your run? Again, that depends on your cell type and as well as the budget. The best and the most optimal method is to use individual thermal mass flow controllers, or TMFCs, which will measure your gas flow rates and are calibrated for each specific gas. However, these TMFCs are costly and budget often dictates how many TMFCs should be chosen, along with, of course, the cells that are being cultivated. Gassing modules usually have 1 to 4 automated gas mixing, meaning that depending on the cell line requirements, the module itself will control the gas mix or the incoming gas composition. So for example, for a typical aerobic microbial culture, we often require air and oxygen for DO control. And for cell culture operations, we typically use air and oxygen as well as optionally nitrogen to control DO. But we then also use carbon dioxide to control the pH. For certain gas fermentations, you may need to use explosive gases like hydrogen, methane, etc. So whether to use 3 or 4 gas controls can depend on the cell line as well as the budget restrictions. Next, we come to the question whether we need to measure exhaust gases. So measuring exhaust gases can give information on metabolic data of your cells. It can be a very powerful tool for troubleshooting and determining respiration rate, the oxygen uptake rate, as well as the carbon dioxide production rate, which in turn will provide a measure of the metabolism of the cells. Now in cell cultures, however, the status of the bicarbonate buffer and the carbon dioxide input from the pH control both should be considered for the calculation of CPR. Standard fermenters are equipped with instrumentation used in control loads, which means that these factors can keep the controllable conditions of the fermentation constant. So for example, flow rates of the feed and exhaust gas, or the pressure in the fermenter, pH level, DO, as well as temperature. Now, online or off-gas analysis can be an integral part of such a standardization, since it allows vital process parameters like biomass development, substrate consumption, or product formation to be monitored. Now, this type of a method also allows fast and direct intervention into critical process stages. Off-gas analysis is often used to monitor biomass growth rate, substrate consumption, and product formation, but it can also be used to for the DO probe functionalities or any upscaling of your experiments, or if you wanted to document the sterility results. Again, here we have a QR code. If you wanted to scan it to access our application note on using exhaust gas analyzer for a PICIA Pastorus run. So next we come to a very important question. How do we calibrate the DO sensors, especially if nitrogen is not available? So a typical DO calibration requires 2-point calibration, which is one to set to 100% DO with air and then set to 0% in an oxygen-free environment. So in general, you don't have to use pure oxygen for DO probe calibration. During your cultivation, you may want to maintain a certain level of oxygen concentration, which could correspond to, let's say, maybe 30% or 60% of the air saturation, again, depending on media composition, temperature, agitation that you are using. Furthermore, some DO probes or transmitters cannot actually measure the oxygen saturation concentrations in terms of pure oxygen. So another important point is this carbon dioxide stripping. When using CO2 for pH regulation and then introducing high amounts of nitrogen could lead to high usage of CO2. So typically, when you are using an electronic zero, that is unplugging the DO sensors to set to a 0% signal, it is not usually recommended and is no longer possible, honestly, with the modern sensors. So nitrogen gas is the most common method to achieve a 0-point calibration. However, in absence of nitrogen, you can also use CO2 for achieving 0% DO. All in all, always calibrate the DO sensor after the sterilization at process temperature and agitation that you will use in the run. Here's another QR code for you that will guide you to our application note, which is a brief DO calibration guide. Next question is how to assure that pH measurements are accurate. So a standard analog pH sensor is usually calibrated before you insert the sensor and sterilize it with the vessel. So what happens is a pH sensor health depends largely on the maintenance and storage conditions of the sensor. Typical storage conditions are potassium chloride solution when you're not actually using it. During the process, it is recommended to take daily samples just to correct the pH if required. And for cleaning purposes, at the end of the run, you remove the pH sensor from the vessel and clean with water or alcohol for disinfecting it. Here's another QR code to access an app note that we have on this topic. Another big question is, how do we measure biomass in the run? So again, this largely depends on the process requirements and budgetary restrictions. There are two methods to measure biomass. One is the online method, which requires no sampling, meaning that it involves the use of inline sensors that can be either invasive or non-invasive. Now, these sensors will read biomass in real time and provide feedback to the controller, which can then be used to set up any automated feeds or other controls. So, for example, capacitance probes like Aber, Futura, or Hamilton Insight. The other option is to use offline methods. So like sampling from a reactor, which is basically retrieving a sample from the vessel and then using offline cell counters like CDEX Bio or Viscous to give you the biomass readings. So this method is much cheaper compared to an online or inline sensor. So let's now move on to the bioreactor or the culture phase, where we actually inoculate and monitor or control the cell growth. So during inoculation, it is important to consider what cell densities to use for the inoculum. So in a typical microbial culture, inoculation ratio is typically anywhere from 1 to 10 to 1 to 1,000 a range, which means for otherwise, on the other hand, for the cell culture operations, it's usually 1 to 2 or 1 to 10, which can be quite a broad range depending on what cell type you're using. Now, the aim is to choose the optimal inoculum such that the inoculum volume in itself in a fermentation run can be targeted to be up to from 0.1 to up to 10% volume. And for cell culture runs, the target inoculation volume would be about 10 to 25% of the starting volume. So two key things to keep in mind during the cultivation phase are the process controls and the process strategy. So controlling the key parameters of the bioreactor, like temperature, pH, dissolved oxygen, agitation, and pressure, are essential to maintain cells in a physical and chemical environment, optimizing their performance. So that's the part that we'll take a look at in the next few slides. So one of the most common questions is how to handle excessive foaming in bioreactors. The most common method is to use anti-foam agents that will reduce the surface tension on liquid interface and break up the bubbles in the liquid surface. However, of course, using excessive anti-foam agent can actually lower the OTR in the vessel and negatively affect DO levels. So in most applications, using anti-foam agent doesn't have a negative or a toxic effect on the cells. However, a lot of cell culture applications don't actually want to use anti-foam agents due to potential downstream separation issues. Other alternatives to using anti-foam agents are either using a lower agitation or testing a different sparger. So like we discussed before, a microsparger could lead to more foaming compared to a macrosparger, or even moving to overhead gassing instead. So however, of course, this approach only works at small scale working volumes. And once you move to a larger scale, you will absolutely have to sparge to meet the DO demands, depending on, again, your cell type and process. Now, foaming can be monitored with the help of level sensors that can distinguish between foam and a liquid. So once a foam is detected by the sensor, a pump can start that will add an anti-foam agent. This prevents foam out events and is especially useful when you're running longer experiments overnight or over the weekend. Next, we come to the strategies to facilitate pH control. So two critical factors that govern cell culture yield are the levels of dissolved oxygen or DO in the bioreactor and the pH of the culture. So for pH control in fermentation culture, we typically use acids like sulfuric acid or phosphoric acid, as well as a base like sodium hydroxide or ammonium hydroxide. Both this acid and base feedback is cascaded or programmed into the pH response mechanism in the controller. So in case of E. coli, the culture usually tends to become more acidic as the OD increases, and therefore you only need a one-way pH control in the form of a base and no acid for such runs. Tight control of your pH with carbon dioxide flow is very critical in cell culture operations, where introduction of acids and bases tends to achieve this desired pH level is often too harsh for the delicate mammalian cells. So in these cases, using CO2 can often help maintain pH. Next, let's look at, this is an example of a feedback loop for using one of our controllers, which is a Saverio twin controller, using a 1 liter glass vessel. We can see how precise and tight pH monitoring or maintenance has been using acid and base in this case. So this is again for a typical E. coli run. So oxygen is another parameter that needs to be carefully controlled in most cultures to get a successful run. Now, In a classical E. coli fermentation process, oxygen is generally the limiting factor. So therefore, using an optimized gas flow rate is very important to maintain a healthy culture. So for this, it is important to use appropriate gas flow rates which can meet the demand of your culture. So for a microbial run, a good rule of thumb is to start with a 1 VVM or 1 vessel volume per minute, and then optimize as required. On the other hand, if you look at mammalian cell culture, you can look at starting with maybe 0.1 to 0.3 VVM gas flow rates, since the oxygen demands will be largely different from a fermentation run. Along with the cell type, gas flow rates you select will also depend on the sparger selection, as well as the impeller type you use, as both of them will actually affect your oxygen transfer rate. As you can see here, the amount of oxygen needed for aerobic microbial organisms is up to 20% higher compared to cell culture runs. So, how do you control your DO? So a typical way to ensure sufficient oxygen supply to the culture is actually displayed here in a 3-step control. So gassing with pure oxygen from the beginning would be possible and would honestly give you much quicker results. However, it is also very expensive. So a frugal way to maintain DO concentration is by increasing agitation rate of the impeller in the beginning. And once the maximum agitation has been reached, the next step is to increase the gas flow rate of air supply. And as a last step, the amount of oxygen in the gas is increased until the maximum has been attained. Looking at a typical cell culture run instead, one is limited in increasing agitation rate or gassing because both of these will lead to shear stress. So the DO control cascade then needs to be optimized accordingly. So this is one of the most commonly asked questions. Does pressure in a bioreactor affect your culture? And how much pressure can or should you be applying to your culture? As a general rule, every bioreactor, depending on the type, has a recommended pressure limit. So the main goal in case of small bench scale reactors is to maintain a certain gas pressure so as to prevent any overpressurization of either single-use or glass vessels and prevent any cracking or explosion issues. Usually, pressure in a bioreactor does not impact the cell morphology. However, it is commonly used in large stainless steel vessels which have automatic pressure control in the exhaust lines. So increased pressure is known to dissolve more oxygen. However, it's not something that is recommended for single-use or glass vessels due to safety issues. Now let's take a look at the different process strategies that you can use to improve your run or your yield. So depending on the cell type and culture goals, different process strategies can be employed to improve growth yields. Optimizing the culture nutrient supply is key in bioprocess development. So in the course of your run, nutrients are consumed and metabolites accumulate, which could end up being the rate limiting factor in your run. So if you look at the graph here, we have a typical simple batch run in which the culture and your cells and media are added to the vessel, and the cells are allowed to grow up until the point that the nutrient source gets depleted, and then the accumulation of the toxic metabolites becomes a rate limiting factor, which would then mean that you need to harvest your cells. The other strategy is to use a fed batch process in which you start off by adding your cells and media to the reactor and allow the cells to grow until the nutrient source is completely depleted. So then at this point, you would end up adding a concentrated feed to the vessel to give it a little boost to grow and give you a larger yield. But even then, after some point of time, the nutrient source could get depleted, and then the accumulation of toxic metabolites could end up, you having to end your run. The third type of strategy is a continuous process in which you constantly add fresh nutrient solution and you are constantly harvesting your culture, thereby maintaining like a steady state. which gives you a constant yield or a constant daily yield. And the fourth type of strategy is a perfusion run, in which you are actually retaining the cells in culture, adding fresh nutrients, and also only removing spent media. So this actually gives you a very high yield because not only are you adding fresh nutrients, but you're also constantly removing toxic metabolites from your run. So what strategies would you recommend to increase protein yield in bioreactors or for cultivating E. coli? So big part of this process, again, depends on choosing the right mode of your operation. Yield is, again, another question of balance. So here we have an application note and the QR code for it where 3 different modes were compared for E. coli. So a batch versus fed batch and a continuous run. So you can see the differences here in terms of productivity and cost per unit, how different they are in terms of the cost, labor, as well as the knowledge base and growth requirements. And all these factors need to be considered before you actually select the best mode for cultivation. So next, let's talk about different scale-up strategies when moving from small to large scale. The goal of the scale-up is to actually maintain certain constant parameters in order to obtain a constant yield and product characteristics when moving from small to large scale. So various parameters need to be optimized during scale-up. So typically, one parameter is kept constant while planning your scale-up studies. So for example, impeller, tip speed, or mixing time. So it is a relatively simple technique and cheap. However, it is most useful only when the scales are not too far apart. Next is using volumetric mass transfer coefficient or KLA, which can be kept constant and is typically used in cell culture scale-up operations. So this method is quite elaborate and requires a lot of experimental data to determine KLA. Another approach that can be used for scale-up is to maintain a constant impeller power consumption per liquid volume, or P by V. However, this method requires measuring impeller power number by using a torque meter. But the advantage in this case is that you only need a single measurement per vessel. So please feel free to scan the QR code here to access our application note on the scale-up. Here is a screenshot of our latest BioFlow 720 controller's scale-up assist feature. The best part of this feature is that it allows you to select the scale-up strategy you want. That is either a constant P by V or a tip speed. So the first step would be you select the first vessel type and size you want to use for scale-up. And once you enter the desired P by V working volume and your maximum gas range, the software will calculate all the parameters required to maintain that constant P by V or tip speed at the next vessel scale that you select. Now, because of all these calculations being software-based, it becomes very easy to enter your desired parameters and get automated values for any vessel size that you may want. And here's the QR code of an application note that will showcase the use of this feature. So then our last topic for today is, what do I choose for scale-up, KLA or OTR, and how do I measure each of these? So in case of a typical cell culture operation, KLA is often used for scale-up purposes. So KLA is the volumetric mass transfer coefficient, which measures the capacity of the bioreactor to transfer oxygen into the cultures at any given set of operating conditions. So when you're talking about scale-up of bioreactors, KLA is a very commonly heard term. So a very typical strategy to scale up that kind of shows your KLA capabilities moving from a small scale R&D equipment to large scale production systems. So one of the methods is to measure KLA is the gassing out method. So this method kind of uses the bioreactor to measure the slow oxygen transferring. So you're measuring the absence of oxygen by gassing out with nitrogen. Whereas on the other hand, when you look at OTR, which is commonly used for microbial cultures, you have sulfide depletion method, which is used to measure it. This method is actually a chemical reaction-based method in which you're stripping the vessel of oxygen by using sulfide depletion to then measure the OTR values. So here are again QR codes for the respective methods, how to determine the OTR or the KLA if you wanted to scan them. And then lastly, the idea and the goal of a successful scale-up strategy is to think about scale-up right from the small-scale R&D cultures. Once you have scale-up considerations in mind right at the small scale, it becomes relatively easy and a smooth process to move from a small to a large scale. So always keep it in mind right from the beginning. That brings us to the end of our webinar. Thank you very much, everyone, for tuning in, and we can take any questions now.
Thank you very much for your presentation. Indeed, it is now time for our Q&A session. Just a reminder for the audience that in order to send in questions, you can do so via the Q&A widget. Your questions will also be available to be answered on demand. It looks like we've got some questions coming through already. So the first one for today is, does the material and shape of the vessel have any influence on the growth of cells?
Definitely. So selecting a material that is chemically inert is important. So for example, stainless steel or borosilicate glass, polystyrene or silicone. Especially for single-use vessels, certified quality will mitigate issues with leachables. There's also a question of whether to use rounded or flat bottom vessels, which one is better. So for kind of the round bottom vessels will give you an improved flow behavior. But when you look at the flat bottom vessels, they have minimal influence on the flow behavior, but they stand better. So again, reactor and impeller geometry will team up in flow dynamics. So it's important to consider all these factors.
And for shake flask, maybe to add, usually you have glass or traditionally disposable Erlenmeyer flasks are made of polycarbonate, like PC. Also, when you have very sensitive clones, there are also materials like PETG, which are bisphenol A-free, so a BPA-free variant you may choose when you have very sensitive clones. So also different options from shake flasks.
Thank you very much. The next question that we have is, what is the optimum way to transfer the inoculum from shake flask to bioreactor?
So this will depend on the volume that we are looking to transfer. If it is less than a 50 ml transfer, then moving from a pre-culture in the shake flask to a sterile beaker and then drawing up the required volume in a sterile syringe. And then you can inoculate your bioreactor via the sampling port on the head plate. However, if you have higher than a 50 ml culture, then you can look at using peristaltic pumps on the bioreactor for larger volumes. So you can use like a sterile welding sterile welding your tube to it and then inoculate accordingly. You also have shake flasks which are available with transfer caps that can be used for this.
Thank you very much. The next question that we have is there a possibility to measure the KLA in shake flasks as well?
Yes, sure. You can also measure the KLA in shake flask, meaning the maximum aeration capacity of the system for the given set of operating conditions. That can be definitely helpful for optimization of pre-cultures, or also if you have any issues with process transfers between shakers and bioreactors. As you know, they have shaking and steering often is the difference, so you may encounter problems, and keeping the KLA constant is one good strategy. In Erlenmeyer flasks, you can also or first maybe the vessel design, fill volume, RPM, and orbit are influencing, and you can determine the KLA value as well, same as with bioreactors or fermenters using the gassing out method, or if you don't have nitrogen gas access, the sulfite method suitable for use with buffer. And also, you need DO measurement, and therefore there are different systems available, for instance, pre-sense systems for measuring DO, so dissolved oxygen and shake flasks as well.
Thank you very much. The next question that we have is, how long does the sensor calibration take for setting up a bioreactor? Does this have to be repeated for every batch setup?
So if you're working with standard ISM or analog sensors, you need to do at least, depending on the type of the sensor that you're working with, you could look at anywhere from 2 to 6 hours of polarization prior to the calibration. I would also recommend that you always change the electrolyte solution prior to each run if you're working with a polarographic sensor. In theory, you just need to do this after it's a better practice to kind of check it every time before you set up your vessel. When it comes to pH sensors, it again depends on the sensor type. A standard gel-filled glass probe needs to be connected to the controller and calibrated before you insert it in the vessel and autoclave the assembly. Again, I recommend to take some time, especially when you start the calibration. Insert the sensor into buffer solution 7 and wait at least, a couple of minutes or 5 minutes or so until the values for the pH sensor will stabilize. The idea is that if the sensor is actually hydrated properly and stored and maintained correctly, then you should be able to avoid fluctuations during the calibration process. In case you are working with optical pH sensors, it is again very easy. Just plug it into the controller, type in the information from the vessel or the sticker on the vessel, and you're good to go.
Thank you very much. Another question that we have is, which impeller is suitable for stem cells?
So if you want to work with stem cells in a bioreactor, you can look at using a pitch blade impeller or with our recently launched 8-blade impeller. So the pitch blade impeller generally is a good choice for shear stress sensitive cell lines. So that will keep your cells in solution at a lower RPM. Now, the 8-blade impeller I just mentioned was especially developed for cultures which are cultivated on microcarriers in solution or in form of aggregates. So this impeller will keep your aggregates in suspension, again, at a very low stirring speed. So you can choose between these two.
Thank you. Another question that we have is it possible to cultivate adherent cells in a bioreactor?
Yes, absolutely. So there are a couple of options here. So depending on the type of cultivation or your cell line, you can either look at using fibrocell discs, which are typically could be used for vaccine production, or you can use microcarriers as the support matrix on which the cells can be grown in these stirred tank reactors. So depending again on the process strategy, like if you want to do a batch run versus if you want to do a perfusion process, you can also look at using different impeller types like a spin filter impeller, which can retain the cells in your bioreactor and just allow you to remove your spent media. And then, of course, you can add your fresh media. So you have a different couple of options here depending on the strategy that you choose.
Thank you very much. And the final question that we'll have time for today is, we experience cell clumping. We use mammalian cells in shake flasks. Is there anything that we can do?
Yeah, shaking already is helpful. I would say better than static incubation. It prevents sedimentation and cell clumping. But of course, with mammalian cells, also the issue is that you cannot go to really high RPM. So you encounter usually cell clumping and sticking on the sides and on the wall when you go to higher densities. So it's also when it's on higher densities, you have more dead cells and debris, free DNA in the media, and also media components may enforce clumping. So possible solutions would be, of course, passage your cells earlier before reaching these high densities. Here it's really hard to give a recommendation. Adjust the fill volume to lower, adjust the RPM maybe to slightly higher. Baffled flask could be a solution, and but when you have like protein expression protocols, also they say it's not impairing the performance. So ex vivo system, for instance, so just allow clumps to settle and take from supernatant. Yes.
Thank you very much. Just a reminder for the audience that if your question did not get answered today, all questions will be available to be answered at a later date, and you can still send in questions on demand. So that just leads me to thank Ines and Ankita for this presentation, and to Eppendorf AG for sponsoring this session. To the attendees, you will receive an email telling you how you can access the on-demand version of this webinar, or you can access this through our website, which is www.business-review-webinars.com. We look forward to sharing further webinars with you, so please do keep an eye on the website just mentioned, and you can also follow us on Twitter at BRWebinar, or join our LinkedIn group Business Review Webinars for daily updates. Thank you all once again, and I hope that you have a great day.